Okay, welcome to our next talk. Being a musician set this speaker on the path for becoming a software developer. Now he's here ready to talk about applied machine learning in Elixir. Please welcome Paulo.
Morning, everyone. My name's Paulo, and before we get into the talk itself, I'm going to present myself. I'm Brazilian. I'm an electronics and computer engineer. I work at CV Labs as a software engineer, both on backend software as well as embedded software and machine learning. And I'm part of the Numerical Elixir, or NX, core team. And before we talk about what NX is, let's talk about why you would want to use NX. So there's basically two reasons, main reasons. One is you find that Elixir is the right tool for your problem. And then you find out that you also need numerical calculus, machine learning, that type of stuff. NX can solve that problem. Or you want to do the numerical stuff, but you don't want to deal with object orientation and data mutations like you get in Python. Then NX is a possible solution for that as well. And NX is both the core library as well as the name that we use for the ecosystem of libraries in Elixir. It was started by José Valente, who is the creator of Elixir, and Sean Moriarty. And as soon as that went public, I jumped in and have been a contributor ever since. It was inspired by NumPy and especially JAX for its functional data structures. And NX then enables all types of numerical calculus in Elixir through special backends. We have quite a few libraries in our ecosystem. So we have NX as our core library. That's what defines the new semantics for numerical stuff. Then we have Axon building on top of NX for neural networks. And then on top of those abstractions, we have Bumblebee that can load Hugging Face models into Axon. So you get all benefits of NX, but you also get to run quite a few Bumblebee Hugging Face models. We also have Explorer for data frames, eVision for OpenCV bindings, Scholar for your classical machine learning, so that's linear regressions, clustering algorithms, some types of interpolation we have there as well. NX Signal contains a currently partial port of SciPy Signal. VegaLite and Toucan we can use for plotting images, plotting graphs, and so on. And Brain for reinforcement learning. So you can also do some more basic types of reinforcement learning directly in Elixir. Oh, and all of these libraries, you can find them on HexPM, which is the official package manager for Elixir. And on HexDocs, you get their official documentation. So, for instance, Bumblebee, we have the documentation here. And you can see that it's basically 2 lines for loading the model, and then other 2 lines for calling the model and getting outputs. So it's pretty easy to get things from Hugging Face into NX. And that being said, we should talk about how NX works. So as I've said, NX will provide new abstractions in Elixir for calling into numerical calculus. So we need new data structures because Elixir will only have, for instance, linked lists. We don't have arrays in Elixir by default. And NX provides tensors for that. And we also provide what we call an NX-defn expression, or defn expression for short. And that's our NX AST. That's how we symbolize our computation graphs. So when you call an NX function, a defn, as we'll see, we first traverse that definition with the NX-defn expression backend and get a full representation of that function. And then we can either traverse the defn expression or compile it down to native code and then execute it. And then we have configurable compilers that will be able to target different types of devices. So NX-define expression will allow us to JIT compile stuff. We can also do some symbolical manipulation. So I'll show a bit how we can do automatic differentiation in define functions. And after compilation, you can compile things to GPU, CPUs. Depending on the compiler, you can also target WebAssembly, iOS runtimes, and we'll see these shortly. NX will, by default, come with basically two backends, which are the NX binary backend. It's the default one. It's written in Elixir, so it's not as efficient, but it makes for a nice interface for doing first tests, because you don't have to compile anything, you don't have to install anything else, it just comes with Elixir. And NX-define expression is this meta backend that we use for tracing and then doing symbolic manipulations. For backends and compilers, we have quite a few of those. I've listed them here. EXLA is powered by OpenXLA. That's the same thing that powers JAX and TensorFlow. And we can target mainly like your generic CPU, x86, ARM, Mac CPUs as well, CUDA GPUs. There is some support for ROCm, but it's not there. It's not as good as the CUDA support. TorchX has basically the same level of support for all of these architectures. There is some support for Metal as well, although it's not as tested in NX. And it's built on top of PyTorch. And currently, we mostly maintain it because that's a backend that we can get to run on Windows. So you can also, if you're using an Elixir directly in Windows without WSL or anything like that, you can use PyTorch directly there. NX Erie uses the Erie compiler and runtime for targeting quite a wide range of architectures. It's a bit slower, but if you're targeting something that you can't target with other backends, it's worth it. So that's how I was able to run NX code on the browser via WebAssembly, or on iOS devices via LiveView Native, which is a separate library in the Elixir ecosystem. And finally, UMLX is powered by MLX, Apple's library for machine learning. So it's the best way that we can support Metal, so actually use Mac GPUs. And now we're going to use Livebook for a demo on how NX works and how to use it for actually getting things to your web application. So Livebook is our interactive notebook for Elixir. And here I am installing the libraries that I'm going to use throughout the presentation. And one that's not directly related to any of the machine learning libraries is this Phoenix Playground, which I'm going to use just to provide a very quick and dirty server that we can interact with. And here I am configuring both the compiler, the default compiler, so everything that we compile by default will use EXLA, which means that it's going to target by default on the Mac the CPU, but this is good enough for us here. It's a very small model that we're going to work with. And I'm also setting EXLA as the global default backend. We also have default backend, so I could have done this, but global default backend will set things for all processes. Elixir is a language that is concurrent by default, so everything runs inside a process in the virtual machine. So I need to think about whether I want to set the defaults for just one process or for the whole VM. In this case, we're setting it for the whole VM. And now we can look at how an X looks. So we import an XDefn when defining our Elixir module, and then that will bring us the defn macro, which will let us define a function in Elixir, but instead of using the default Elixir kernel, the defn macro is going to override it with the nx-defn kernel. So it's going to use the definitions in this module, which means that if I'm using the plus operator, that's not the default plus operator if either of the operands is not a compile time number. That's going to become nx.add. So if I instead did something like nx.add, that's exactly the same thing. And then we're returning a tuple. I'm just returning a tuple so we can see different defn expressions and how they look and how we can deal with gradients over functions that do return more than one position as well. And yeah, when we call our defn, numbers will become tensors, and then each input will have its own inferred type. So by default, floats are inferred as float32. I could use like the F64 helper to force it up to F64, and then we get something like, hey, this cosine is only operating on X, so it's going to just take the precision of X. The sine will just take the precision of Y, and Z1, wait a second. And then Z1, because it's working with both numbers, then it's gonna upcast to F64, and then the results will be working on F64 from there onwards. So we can see this here. Z1 returns F64, and then we have one F32 and one F64 for each of the inputs. And NX also has automatic broadcasting. So I have a one-dimensional tensor, a vector here, operating with a scalar, and we can see that the result takes the same shape as the vector because we can broadcast, we can kind of distribute over the scalar number to the vector. And then just talking about the representation here, we have our data type followed by our shape. That's basically how many elements we have and how they are distributed over dimensions. Then EXLA also adds a backend header so we can see, for instance, which device it's using. Host is the CPU. And then we can have the preview of our data or the full data if the tensor is small enough. However, we can also use defn debug expression over our function. And then for the case where we have two scalars as inputs, we can see the actual symbolical representation. This is what I was talking about. We first get this representation and then we execute the computation, which means that we have all information here for doing automatic differentiation if we want to. And this is exactly what we're doing here. So we're calling an xdefn grad, and then we're saying, hey, let's calculate the gradient over each of these variables. So we're going to first see how they propagate over through the expression, and then I have to do the nx sum here because the defn grad requires a scalar output. And then when we calculate this result, we'll see that if we recall, our expression is just cosine of x plus sine of y. So the expected gradient would be for x minus sine of x and for y, the cosine of y. And this is exactly the result that we get from our Devin expression grad. And this is actually how Axon, or neural network library, is able to do training. We define the functions with Devin, and then by default, we already have the gradient definitions. We can also do custom grad if we know that a given function will have a special definition for gradient. But if you don't define that, we can calculate that automatically. And speaking of Axon, let's create a simple neural network with it and then plug it into our Phoenix simple server. So here I'm just generating random data for our training. And the operation that we want to approximate is the logical XOR, so just X XOR Y. I'm just generating random zeros and ones and calculating the XOR over each pair, and that's the output. And we're returning these in a list. So if I generate 1,000 of those, I get a list that looks like this. So we have a map with keys of X and Y, each one with its own value. And then as a second element in the tuple, we have our expected output. So that's our inputs and ground truth for training. And here is how we define the neural network. So we're just saying, hey, this network has one input called X that has a batch dimension and then one dimension with size 1. Same thing for Y. We concatenate both of those and then just define 2 dense layers, really simple neural network. And because we know that the output is limited between 0 and 1, we just use the sigmoid function, activation function, for the output. And this is our model. We can visualize it with Axon display as graph, so we can kind of see the same definition that we had there. And I want to highlight how nice it looks to define a neural network with the sequential layers using the pipe operator in Elixir. This is actually one of the things that I like the most about using neural networks in Elixir. And now for training, it's as simple as this. Axon does provide our loop trainer helper, so we just have to pass in the model, define the type of loss function that we're going to use, the optimizer, and for the default functions, we can just use atoms, and then Axon can convert those to functions that it knows. But you can also do custom functions as well. And then we do loop run with our data. We initialize the model state as empty. If we had it saved to some file, we could have loaded it here. And then we're just running it over 10 epochs. So if I just run this, the model is trained. And then we can do inference. So I'm just defining all of the 4 possibilities that we get for X and Y. We can either use Axon build and get a predict function, and we're going to use this soon. Or we can call Axon predict with the model state. This is the trained model state. This is just the model definition. And then the inputs that we want to predict. And then we know, because we know the operation that we're approximating, we also can check it against the actual values that we should have gotten. And I'm just defining an Explorer data frame here because on Livebook, if you return a data frame from the cell and you have Kino Explorer installed, you'll get this nice visualization. So we can see our things in a table. So we expected 0, 1, 1, 0. We got things that were pretty close to that. Note that this is 0.08 something. And then, 0.0008. And then if we apply a threshold, so just compare it with 0.5, we'll get exactly the result that we expected. we're training with much more data than what's needed. It's very overfit, but it's a toy example. And then NX does provide the NX serving abstraction, which you can read about in our documentation. And the NX serving in this type of usage will allow me to start this as a process that's registered to the my serving name. And then I can have multiple web clients connecting to my server. And then each one of those is going to have its own input, but then the serving is going to receive all of those inputs batched together. It's going to run the network over the batch, and then the results are unbatched to each caller. In our case, we're just going to use a batch with one element. And then from that batch, we can extract X and Y, pass them over to the predict function that we got over up there, and then apply the same thresholding. And this should get us the XOR for the inputs that we have on our web layer. And I'm not going to go over the live view definition. This code is available on GitHub, will be available on GitHub. But just know that we have X and Y as part of our state. Result is also part of our state. And then I'm just defining like the markup for the view that we're going to be interacting with. And then live view can react to clicks. And whenever we get a click on our checkbox, we're going to toggle the saved result, the saved state, calculate a new result for the operation given the state that we have, and then update that saved state for the result as well. And then if we just compile this, run the live view, and go over to our page, as soon as we click, we get a reactive page that's actually using machine learning features in Elixir. And just to close our talk, I'd like to thank you for being here. This is the repository where I'm going to be publishing this, both the presentation and the code, as soon as we're done with the presentation. Thank you.
So we have a limited amount of time if anybody's got a quick question. Yep.
When I've played around with this in Python, go and start running, and then it just blows up with errors that you have no idea how to look into. How do you guys help with that? Or is the kind of life cycle a little easier to work with, or how does that work?
So Elixir does recover from errors quite well because of its process structure. We use supervisors to kind of restore process. So if you just get a simple one-off error that's already handled by Elixir, we are working, we'll be releasing this probably next week on GitHub, a debugging feature for the NXDefn evaluator, which is like our default compiler, which will allow us to at least get results at each step of the defn graph. And I'm actually introducing that because we have some part of EMLX that's not working, and that the same function works with EXLA. So I have like the ground truth, I have the broken results, and I need to figure out where it's broken. So we're going to have that. And we can also do some basic introspection with print value as well, which is a function that we have on an NXDefn kernel.
Okay, let's give him a final round of applause, and you've got about 3 minutes to get to the next talk.
Thank you.